Good evening, ladies and gentlemen. How is everyone doing? Did you guys have a good recess? Okay, so seeing you had a bit of work to do over the recess for most of your other modules. So tonight's lecture is not going to be a long lecture. I plan to end this lecture at 6:30 because I'm attending a conference this week and I'm giving a talk at 7 o'clock this evening. So to end the lecture at 6:30 gives me enough time to give the talk at 7. Yes, thank you. And then one other thing I would like to add for your moon assignment. Have you guys used Turnitin before? Okay, so for the moon assignment, you're going to submit it via Turnitin. So university policy is you cannot have more than 30% similarity. So that means more than 30% plagiarism on your assignment you are submitting. Each faculty and department can change it a little bit. Some departments can even make it as little as 10% as long as it is below 30%. So it depends on department and faculty. But for us, we're going to stick with the general university guidelines and no more than 30% plagiarism. Plagiarism is a very, very, very important aspect of your academic career and studies and also your professional careers. If you're caught with more than 30% plagiarism, the minimum sentence, I would like to call it sentence or punishment, is to be expelled from all academic institutions for a minimum period of 2 years internationally. So it is very important not to plagiarize your work. So in the week, I will open up Turnitin. So while you are writing, then you can check your plagiarism as you go along. And then, not to waste time, we can start with tonight's lecture. So before the recess, we ended with nebula and discussed what is a nebula. Are you still happy with what a nebula is? Definition, features? Okay, so let me do a small recap. Okay, so this image is probably the most interesting object to me to observe and my most favorite object to observe. Do you recognize these stars and this constellation? Yes, this is Orion. So these are Orion's belts. The common name for it is the Three Sisters. Over here is Orion's sword. And if you zoom out, you will see his arms. But within Orion, there are a few nebulas. So one is around the star over here. Then the other one is in the center of Orion's sword, and that is primarily known as Orion's Nebula. And these nebulas are interstellar nurseries where stars are born. So this is another nebula. This is the Crab Nebula that went supernova. It started went supernova in around the year 11,000 to 13,000. The Chinese has documented it extremely well. When it went supernova, it was visible for a couple of years as a star in with your naked eye. And when you look through a telescope, this is what you see. So this is the remnant of the supernova, and we can still observe it today. This is inside the Orion Nebula, and this is a question. I was out of the city the past week and tried to see the nebula, but I couldn't. Probably need a telescope. Yes, you will need binoculars at minimum to see it. So in Orion's nebula, so this is the nebula not in the belt, not in a sword, but on the belt. You get the Horsehead Nebula in Orion. And then there's also an interesting nebula we can observe, the Hourglass Nebula. So putting this together, what is a nebula? So number one, its H2 regions are clouds of gas ionized by the ultraviolet radiation from nearby hot stars. They are often called emission nebula because the ionized hydrogen produces visible wavelength photons that make the regions glow with a characteristic pink color. If nearby stars are not hot enough to ionize the hydrogen in nebula, it may still be visible as a reflection nebula, produced when light is scattered by tiny dust particles mixed in with the gas. And thirdly, at visual wavelengths, dark nebulae are visible where dense clouds of gas and dust are silhouetted against background regions filled with stars or bright nebula. So a nebula is used for star formation. So a nebula in space, you can think of it as a giant molecular cloud. These giant molecular clouds are created in supernova explosions in areas where there is immense gravitational pull, or where certain objects passed through and has broken up due to gravitational pull. So how does nebula fit in to create stars? Why do we call nebulas stellar nurseries? So in the next image, we're going to see a giant molecular cloud began to collapse and form stars in a few million years ago, including 3 massive star clusters visible in this image. Intense radiation outflowing gas from the hottest, most luminous of the stars is exciting some of its gases to glow as an emission nebula, and is eating into a remaining dark molecular cloud at right lower end. The NGC 346 nebula is located in a small Magellanica cloud, a satellite galaxy of the Milky Way, about 60 parsecs or 200,000 light years from Earth. Are you guys familiar with the Magellanica clouds? So the Magellanica clouds are small galaxies also close to Earth. So the closest galaxy to Earth, our closest galaxy to the Milky Way, is the Andromeda galaxies. But two other galaxies that is much smaller than the Milky Way and Andromeda is basically satellite galaxies because it orbits around our own galaxy, are the Magellantic Clouds. They are the large Magellantic Cloud and the small Magellantic Cloud. If you are at extremely dry places and cold places and places where you have a clear view of the horizon, if you look south with your naked eye close to the horizon, you will see two small clouds near the horizon, and that literally isn't clouds. Those are the small and large Magellanic Clouds that you can see in the south. But again, you need some really good atmospheric conditions, and you need to be quite high up so you can look close to the horizon to be able to see them. But if you have binoculars or a small telescopes, then it's quite easy to find the large and small Magellanic Clouds if your horizon is not obstructed by something. So here is a visual in infrared. So here we can see these star clusters, another star cluster, and another star cluster. So how do you get star birth in these molecular clouds, or another word for it is nebula? Spectra of the interstellar medium showed that its chemical composition is basically the same as that of stars. By observing at far infrared and radio wavelengths, to which interstellar dust is nearly transparent, astronomers can peer inside even dense molecular clouds and find evidence that stars are forming there. In fact, the largest molecular clouds are each massive enough to make thousands of new stars. Nevertheless, such a cloud can form into stars only if small portions of the cloud can be compressed somehow to high density and high temperature. So always keep in mind, the two important factors here are density and temperature. At least 4 factors resist the compression of an interstellar gas cloud, and those factors must be overcome by gravity before star formation can begin. And here are the 4 factors. So firstly, thermal energy in the gas appears as motion of atoms and molecules. So remember, what happens when you heat up an object? If you heat up an object, its molecules start to vibrate more and move more, and that is what heat is essentially. So the thermal energy in these gas are the motion of the molecules and atoms that is rubbing against one another. This thermal motion would make the cloud come apart if gravity were too weak to hold it together. Secondly, the interstellar medium is filled with magnetic fields. Ionized atoms having an electric charge cannot move freely through a magnetic field. Although the gas molecular cloud is mostly neutral, some ions are included, and that means a magnetic field can exert a force on the gas as a whole. Gravity must overcome the interstellar magnetic field to make the gas contract. Thirdly, everything in the universe rotates. As a gas cloud begins to contract, it spins more and more rapidly, just as the ice skater spins faster as they pull in their arms. This rotation can become so rapid that it resists further contraction of the cloud. Then fourthly, turbulence in the interstellar medium can prevent the cloud from contracting. Many nebulae are observed to be distorted and twisted by strong turbulent currents that can prevent the cloud from contracting. Given these 4 resisting factors, it may seem surprising that any molecular clouds can contract at all. But both theory and observation suggest such clouds can be triggered to form by star form stars by effects such as passing shock wave, sometimes just called a shock, the astronomical equivalent of a sonic boom. During such a triggering event, some regions of the large cloud can be compressed to such high densities that the resisting factors can no longer effectively oppose gravity and star formation begins. So this is a simulation of what happens when a triggering event happens. So here we have our nebula or molecular cloud, and we have a shock wave. These shock waves can occur from supernova explosions, gravitational waves, and a few other things, or can also be a large star that is throwing off a bit of its mass. So we have the incoming shock wave. The shock wave passes through and then compresses the gas. So motions in the cloud continue after the shock wave has passed, and then the densest parts of the cloud become gravitationally unstable. Then parts of this gas becomes to contract, and that gives birth to stars. You guys have any questions so far? So yes, it can give stars birth to many stars. So usually in these nebula, there are thousands of stars being formed at the same time, and each of these stars are in a different part of the formation process. So these formation can take thousands of years and millions of years to occur, or it needs millions of years to form stars. So throughout these nebula, there are different stages of these stars being formed. I hope that answers your question. It's a pleasure. Shock waves that can trigger star formation are common in the interstellar medium. For example, gas flows of several sorts produce shock waves when they push into colder, denser interstellar medium. The ignition of very hot stars ionizes nearby gas and causes it to flow rapidly away, and new stars of all types seem to emit strong winds and jets while they are forming. Supernova explosions create powerful shock waves that rush through the interstellar medium. So here we can see if energy makes the particles to expand, doesn't that aid formation with reference to resistance 1? Yes, it helps in a little bit. So you need the energy, so you need these moving particles to overcome the gravity of the molecular cloud. So yes, it does aid. Yes, Mr. Lubuyo.
So where, so where does the energy come from, like, to trigger all this star formation?
So that energy comes from supernova explosions in the shock wave moving through. So the energy comes from the shock wave moving through the interstellar medium. So that energy comes from supernova explosions or stars that is shedding off its outer layers. And that causes it to drift through the interstellar medium as a shock wave, and a shock wave carries the energy needed. Yes, sir, go ahead.
So, sir, Which gases are ideal for star formation? So, for example, if we have helium and hydrogen, taking into instance that helium is an ideal gas, which gases exactly are most likely to form stars?
Okay, so when we speak about gases in terms of astronomy, we don't really look at ideal gases. We speak of gases as basically elements. So the elements needed to construct, so the elements that is inside a star is already inside a nebula. So primarily, we are interested in hydrogen gas. We need, so to start a star, we need hydrogen fusion. So we will need hydrogen and a bunch of the other elements that's around, if that answers your question. So question, why does supernova explode? We will discuss that in an upcoming lecture. We're going to discuss supernovas entirely. And then, so the death of one star can cause another star to be born. Exactly. So here we can see a nebula. This is an infrared image. So here, dust condenses where the gas is compressed. Then in this region over here, we can see a new star being formed by compression. Then in the image here, we can see location of an ancient supernova explosion. So right here is the arc made by the explosion. So if we move the arc move through the nebula, we can see the arc compressed the gas together. And here it's compressed so much that star formation are triggered in these zones over here. Yes, Mr. Luguio.
So, so I understand the fact that stars form from like these shock waves that are caused by supernovas. But then so like before stars formed, there were no stars and there were no supernovas. So does that mean those earlier stars formed in a different way?
Yes, they formed in a different way. We're going to discuss that in later chapters as well. But that basically comes down to the Big Bang. So when a Big Bang occurred, it has a massive shock waves and that scattered particles throughout the universe. That particles then got excited, got clumped together, formed these and formed stars. Those stars went supernova and caused different other nebula to form, and it's a process that started. But in the Big Bang, in the shock wave of the Big Bang, there was enough material to form the first stars.
And so do these stars still exist now?
Hmm. Some of them may, in the form of brown dwarfs, and the others probably went supernova, and we can see the supernova remnants. And then how would a shockwave propagate through space? Remember when you speak about interstellar space, there are still particles. So usually when you think about space, we think about it as an empty void. There's nothing. But there are still particles in empty space. And that's enough for a shockwave to propagate. So is the assumption that the universe began from a white hole entirely dismissible? That's interesting. So we are still trying to investigate white holes. So I'm not a cosmologist, so that's not my field of expertise, but I will try and find out more about white holes. But so far we look at everything as a model. So we have a standard model. And the standard model explains everything we know about physics. So the standard model needs to explain all the forces we have in physics. It needs to explain all the subatomic particles. It needs to explain energy. So the standard model works nicely with the Big Bang theory. So yes, space is not truly a vacuum. I can't remember which slide, but one of the previous slides, I listed how many particles per cubic centimeters there are in space. Perhaps I can quickly find it. Okay, so I just quickly searched. So in space, on average, there are 0.3 atoms per cubic meter. Yes, Mr. Levuyo.
So the shapes of those nebulas, are they so since there's like no molecules surrounding those nebulas, right? Well, there is, but like it's not enough to cause a pressure that's noticeable.
No, so when we look at the infrared, so the brighter the colors in this image, the bright intensity of the infrared radiation we can detect. So when we looked outside of the nebula, or right in the middle of the nebula here, we don't see any bright intensity, meaning the particles are a lot less, meaning where the bright colors are, that is where the molecular cloud is, and the molecular cloud is the nebula. In the image to the right, we can see there's not enough particles on the outside of the nebula, but inside we can see high intensity infrared in the molecular cloud, meaning there's a lot of energy in the molecular cloud we can detect in certain wavelengths.
Yes, sir. Yes, sir. That's what I'm saying. So like, there's not enough clouds. Like for example, like where it's dark, there's not enough particles to like.
Yes.
So then, so that means there's no pressure from like the space around it to actually um give it a shape. Is like the shape, it's purely from the gravity in which the particles are interacting with one another.
Yes, that's exactly it. And when a shock wave moves through the area, the nebula is distorted a bit and its shape can change. And then
Thank
also
you, sir.
remember, in this nebula, because we have now more molecules and particles clumped together, they have a gravitational pull of their own.
Thank you, sir.
Pleasure. So now what happens inside this nebula? So in this nebula, before we can have a normal star, a protostar needs to form first. So the planets form as a result of intense compression. Yes. And we're going to discuss that in a later lecture as well. You can understand how low density clouds of interstellar gas might contract to become as dense as stars. But how does the cold gas become hot enough to be a star? The answer is once again gravity. To see how gravity can heat the gas, shift your attention to one dense cloud core, destined to become a single star. Once that small cloud of gas begins to contract, gravity causes the atoms to fall towards the center, gaining speed as they go. Astronomers refer to this early stage in the formation of star as free fall collapse. By the time the atoms has fallen most of the way to the center of the cloud, they are traveling rapidly. The atoms begin to collide with one another and convert the inward motion to jumbled random motion of thermal energy, causing the temperature of the gas to increase. When the contracting core becomes hot enough, it produces short wavelength radiation to which the core is not transparent. The core's thermal energy can no longer escape and it enters a new stage of slow rather than free-fall contraction. Although the term is used rather loosely by astronomers, a protostar can be defined as a stellar mass object that is compressed and hot enough to be opaque to the radiation it's emitting internally, but not yet compressed and hot enough to be able to generate energy by nuclear fusion, as would a main sequence star. Instead, a protostar shines with energy released gravitationally from a combination of matter falling inward to the protostar, plus slow contraction of the protostar itself. So question, funny it sounds like magic. How does gravity get the pulling energy? Sorry for overthinking. Okay, so let's get a whiteboard out. It'd be easier to explain with a whiteboard. So let's make it blue. So let's say this is our compressed gas. Then around our compressed gas is our molecular cloud. So this we can say is full of particles. But these in the center are already compressed and has a gravitational pull. And due to the gravitational pull, the other particles get pulled towards the compression region. And these particles that is now, or molecules that's now being moved by gravity, gets energy, so they get acceleration. Due to the acceleration, they start hitting into one another and causing jumbled collisions. And that motion of collisions is what's causing heat. Does that help in some way? Everyone following? You can go ahead.
Okay, so it does help me understand how the particles, the cold particles, gain energy and stuff. But then the question I'm having is, how does gravity itself gain the force to pull these objects? Because it just sounds like magic that gravity is a god that is able to pull these objects. I'm looking for the origin of that ability, like the origin of that energy.
Okay, so I understand what you're saying. So it's, in the simplest form, it comes down to Newton's laws. Newton has a law of uniform attraction. So stating one body will attract another body. So it doesn't matter what the two objects are. Each object will attract the other object in a gravitational pull. So the Earth have a gravitational pull on the moon, so that's why it's locked around Earth. But the moon has a gravitational pull on Earth, and that is what causes tides. If you have two objects on your desk in front of you, each of them will have a gravitational pull on one another. Because the objects on our desk doesn't have much mass, the gravitational pull is so small it's actually, you can actually just leave it out. But everything attracts one another. So where I'm sitting right now and where you're sitting, we have a gravitational pull to one another. And what happens is in the star formation, how it happens is we have a, let's say, one particle that's a bit larger, one particle that's a bit smaller. And these two will attract one another. So the smaller one will get pulled to the larger one. That will be clumped together and that will form a larger particle. So then around this larger particle, you will get other particles again. That will get pulled to the larger particle again. And then again, you will get a larger particle. And as these particles get larger, the gravitational field gets larger, and the more gravity you have. Okay, cool. I see you say you have a sense of understanding. Does anyone else have a question? Everyone still following? Awesome. So let me find the slides again. Now I can't remember the slide number, but I will find it now. Yes, Mr. Levuyo.
It's just a question about stars. So why like so why do we why do we have neutron stars but we don't have stars made out of electrons?
Okay, that's a very good question. So a neutron star isn't actually made out of neutrons. The neutron star is a star that collapsed on itself. So its outer layers gets blown off and that becomes a supernova, but the center collapses onto itself. So the core of that star becomes so dense that we classify it as a neutron star. And these neutron stars we classify in certain ways that we're going to discuss. For example, we get pulsars, that is a class of neutron star as well. But if the core of the neutron star collapses even further, that creates a black hole that we're also going to discuss in later chapters.
So and when you say the core collapses on itself, does that mean like also the electrons in the atom also collapse in this core?
Yes, exactly. That means all the material in the core, and if you zoom into that material, if you can put it that way, you can see the electrons, protons, neutrons, that also collapses onto itself and becomes an object that's extremely dense, that's a neutron star. And if it collapsed even further, that will become a black hole.
Thank you, sir.
It's a pleasure. So another question. I know they theorize that there is a force carrier for gravity called a graviton, just as the force carrier for electromagnetism is a photon, but it's not proven yet. Yes. Each fundamental force has its own corresponding boson. The strong force is carried by the gluon. The electromagnetic force is carried by the photon. Bosons are responsible for the weak force. Although not yet found, graviton should be the corresponding force covering particle of gravity. Yes. So there's a lot of research going on to gravitons, and that's why we have experiments and observatories such as CERN and LIGO. So, by the time the atoms has fallen most of the way to the center of the cloud, they are traveling rapidly. The atoms begin to collide with one another and convert their inward motion to jumbled random motion of thermal energy, causing the temperature of the gas to increase. When a contracting core becomes hot enough, it produces short wavelength radiation to which the core is not transparent. Then the core's thermal energy can no longer escape, and it enters a new stage of slow rather than free-fall contraction. Although the term is used rather loosely by astronomers, a protostar can be defined as a stellar mass object that is compressed and hot enough to be opaque to the radiation it's emitting internally, but not yet compressed and hot enough to be able to generate energy by nuclear fusion, as with the main sequence star. Instead, a protostar shines with energy released gravitationally from a combination of matter falling inward to produce the protostar, plus slow contraction of the protostar itself. The protostar continues growing deep inside a surrounding cloud of cold, dusty gas. The enveloping clouds have been called cocoons because they hide the forming protostar from view. In this HR diagram has been extended to very low temperatures to show schematically the contraction of a dimmer cool protostar. Then in image B, protostars are normally invisible at visual wavelengths because they are cool objects and are deep inside dusty clouds of gas, but they are detectable at infrared wavelengths. So here we can see the beautiful Orion Nebula. That's my favorite object to observe. And because if we look with optical telescopes, we won't be able to see something because the star will be hidden in its cocoon, so meaning the gas and dust around it. But in infrared wavelengths, we can see the protostars glow red. So here in the HR diagram, we can see the temperature versus luminosity. So as the contracting protostar grows hotter, but is still hidden in its dusty cocoon, and is detectable only in infrared. And then somewhere on the main sequence, a newborn star becomes visible as it blows its dust cocoon away. And that blowing of the dust cocoon away can trigger star formation again. And depending on how big it is and all the factors that we learned, that star will be somewhere on the main sequence. Protostars are not easy to observe. Astronomers calculate that a protostar stage is less than 1% of the lifetime of the star like the Sun. And although that is a long time in human terms, you cannot expect to catch many stars in the protostar stage. Furthermore, protostars form deep inside clouds of dusty gas that block your view at visible wavelengths. And being cooler than full-fledged stars, they produce radiation primarily at longer wavelengths. Astronomers must therefore depend on observations at infrared and radio wavelengths to search for protostars in their natural environment. At the center of the Orion Nebula, also known as Messier 42, you guys still remember my explanation of Messier objects? Yes, Mr. Luyo.
So would you be within these cocoons? So would you be would people in like space rockets be able to go into them and see?
Yes, you will be able to do it. So remember those space cocoons or stellar nebula. is still not as dense as solid matter, so it's somewhere in between solid matter and a gas. So yes, if you have a spaceship, you will be able to go inside a nebula, but the only question is, the deeper you go inside a nebula, the higher the pressure is, the higher the temperature is, and then you will cause all sorts of problems.
And so we know like the conditions within the nebula just by observing the light.
Yes, we observe that we know what the conditions is by looking at all the electromagnetic radiation we can detect from these nebulas.
So even if you don't have information about like the rest of the cloud that's behind of what you're looking at.
Yes, so when you point our telescopes to a nebula, we can get information from the molecular cloud or the nebula itself by looking at its emission absorption spectrums and what's the energy released from these particles. And we can also make use of the same techniques to see what a protostar is up to.
Thank you, sir.
It's a pleasure. So now I have a question. So why do stars burn out? If they develop independent gravities, do external forces overpower gravity? So we're going to discuss that as well in later chapters, the death of stars, and we have done that in the beginning of this chapter as well. But what happens basically in the death of stars is a star makes use of hydrogen or fusion reactions to form its nuclear energy and power. So it fuses two hydrogen atoms to make a helium atom. That helium atom gets fused to make a carbon atom. So each time you go to a heavier element, it's more difficult for the star to maintain that reaction. So usually when we get to heavier elements, the reaction becomes more difficult to maintain. So usually when a star reaches its forming state, which starts to create iron, the outgoing nuclear reaction cannot maintain a gravitational pull from the created elements downwards, and it collapses on itself. A star such as our sun will stop at carbon fusing. So would you say that stars are born faster than they die? Yes, they are born much faster than they die. At the center of the Orion Nebula, also known as Messier 42, lie four brilliant blue-white O and B stars known as a trapezium. The most luminous is a cluster of a few hundred stars. Surrounding those stars are the glowing filaments of a nebula more than 8 parsecs, or 26 light years across. Like a great thundercloud illuminated from within, the churning currents of gas and dust suggest immense power. The significance of the Orion Nebula lies hidden, figuratively and literally, behind the visible nebula. This region is ripe with star formation. So note four important points. The visible nebula is only a small part of a vast dusty molecular cloud. You see the nebula because the larger stars born within it have ionized the gas and driven it outward, breaking out of those molecular cloud. Visual and infrared observations reveal small dusty clouds of gas called Bok globules that may be in the process of forming stars. Secondly, a single very hot and short-lived O star, one of the stars in a trapezium cluster, is almost entirely responsible for producing the ultraviolet photons that ionize the gas and make the nebula glow. This star is so massive that it has already become a main sequence star, while its smaller siblings are still protostars. Thirdly, infrared observations reveal clear evidence of active star formation deeper in the molecular cloud behind the visible nebula. Then lastly, many of the young stars in the Orion Nebula are surrounded by disks of gas and dust. Now this builds up to contagious star formation. Not only can astronomers locate evidence of star formation, but they also have found evidence that star formation can stimulate more star formation. If a gas cloud produces massive stars, those massive stars ionize the gas nearby and drive it away. Where the intense radiation hot gas pushes into surrounding gas, it can compress the gas and trigger more star formation, like a brush fire moving through the interstellar medium. Star formation can spread itself especially by the actions of massive stars, and astronomers have located signs of such episodes. So here we can see star forming region N11b. So in image A, the blast of light and ultraviolet radiation from the formation of an earlier generation of stars compressed neighboring gas clouds and triggered the formation of the stars at the left side of the frame. Those stars are now triggering the birth of a third generation of stars at the right. Note the block globule at the upper right corner. So here we can see massive stars in the region were triggered into formation by compression from the formation of earlier stars out of the image to the left. New stars are forming in these dense clouds because of compression from the stars. Then image B, compression can trigger the formation of very massive star clusters. Superstar cluster Westerland 1 contains approximately 500,000 stars, some extremely massive. It must have formed no more than 5 million years ago. So this is, we can see the star cluster. The history of star formation in the constellation of Orion is written in the stars. Judging from luminosities and estimated masses of the most prominent examples, the stars at Orion's west shoulder are less than 12 million years old, while the stars of Orion's belt are at most 8 million years old. The stars of the trapezium at the center of the Great Nebula are no older than 2 million years. Star formation has swept across Orion from northwest to southwest, apparently beginning near Orion's west shoulder. The massive stars that formed there probably triggered the formation of the stars in Orion's belt. That star formation episode may then have caused the formation of the new stars you see today in the Great Nebula. So here we can see this is the location to Earth. This is the hot trapezium stars, expanding ionized gas, and there are a few protostars. So this is just an artist's representation of what's happening. When most of the material in a protostar's cocoon has fallen inward or been driven away, the protostar will no longer be quite so hidden. The locations in the HR diagram of protostars that have become detectable at visible wavelengths because their cocoons have disappeared is called the birth line. Once a star crosses the birth line and becomes visible, it continues to contract and move toward the main sequence at a pace that depends on its mass. Stars in this late stage of formation are sometimes called young stellar objects, or YSOs, or pre-main sequence stars, to distinguish them from earlier protostellar stages. The more massive a star, the stronger its gravity, and therefore the more rapid will be its contraction. Astronomers calculate that the Sun took about 30 million years from when its cloud began contracting until it became a main sequence star. But a 30 solar mass star would take only 30,000 years. A 0.2 solar mass star needs as much as 1 billion years to finish forming and reach the main sequence. As a contracting molecular cloud core becomes a protostar, the cloud rotates faster and faster. The rapidly spinning core of the cloud must flatten into a spinning disk like a blob of pizza dough spun into the air. Gas from the envelope that has lost some of its orbital velocity through collisions can sink directly to the center of the cloud where the protostar grows more massive. Surrounded by the disk Other infalling material can add to the disk and then move within the disk plane towards the star. So here is our normal HR diagram again. So here we can see how long it would take for a 15 solar mass star to reach the main sequence. And here 0.5 will take 100 million years, 1.6 million years. So the more mass the star has, the faster it's formed and the faster it will reach the main sequence. And here we can see the birth line just before the star reaches the main sequence. So, ladies and gentlemen, I think we're going to call it the evening. Sorry that this lecture is so short this evening. Tomorrow night's lecture is also going to be short. I also have another presentation in this conference tomorrow evening. So sorry about that. I really apologize. If you have any more questions, you're more than welcome to bug me during the day. And remember, you have a quiz this week. The quiz is on all the work we discussed so far. If you have no questions, you are more than welcome to log off. Otherwise, I will see you all tomorrow evening. So can we confidently say the moon was once hot? So yes, the moon was once hot. We can discuss moon formation as well. Yes, you can go ahead. Okay, please explain what a birth line is again. A birth line is the point where a protostar becomes a young stellar object. So just the stage before it reaches the main sequence and become a full-fledged star. So that is the point where the protostar shreds its cocoon, and you can now see it in visible wavelengths, if that makes it a little bit more clear. It's a pleasure. So what happens to the energy in the star when it burns out? So if it goes supernova, most of the energy is blown into space as a supernova explosion, and a lot of the energy is used for the core that falls in on itself and becomes extremely dense, and that can become a black hole, but we're going to discuss that in later chapters as well. Yes, Mr. Luguyo.
So about the about stars, so because we can't necessarily differentiate whether they are a gas or a liquid, so can we say they are a supercritical fluid?
So not really, because majority of these stars, usually their outer surfaces is gas form, and then the gas will become denser, 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 denser until we get to the core. So usually when the hydrogen fuses, it forms a hydrogen core. Then it fuses helium, so helium will be around the hydrogen core, and then it will collapse on itself, and you will have hydrogen core. Then you will have a carbon core, so it all depends on what element is being fused.
But then, so we're not particularly sure what state of matter it is.
So yeah, we can say what state of matter it is, because hydrogen is a gas, helium is a gas, carbon is also is more of a solid. Iron is a solid, so it all depends on how closely bind these atoms is. So yes, you can describe it as plasma as well. Plasma is a better word to describe it.
So depending on which stage it is in its life cycle, it can be like at its core, it can be a solid, but by like on its surface, it's a gas.
Yes, that's exactly it.
But in the beginning stages where it's still fusing hydrogen into helium, it's the core is a gas.
Yes, a dense gas.
Okay, so could you please just explain why the corona is much hotter than the surface of the surface of the sun?
That is still something we are investigating. That's something we're not entirely sure of. So that's why we have solar probes. So I think last one we sent is the Parker Solar Probe. That's investigating the corona of the sun so we can determine what's happening. But it seems like it has to do with the magnetic field lines of the sun, that some of the surface of the sun is pulled on these magnetic field lines, and then instead of going through the full loop of north to south in these magnetic field lines, a lot of this material is dumped in the corona, and that can cause it to be much hotter than the surface. But that's the leading theory we are working with.
Okay, so it says, so I don't want to make you late, so but I have like a sort of like a list of questions.
Do you have your list? So can we, tomorrow night's lecture, before we start the lecture, can I answer your questions then?
Yes, sir.
Okay, just keep them in mind, and then we can discuss your questions first thing.
Okay, thank you, sir.
It's a pleasure. So have a great night, everyone, and I will see you all tomorrow.